Great. So today is our third video of geometry, and today we'll be talking about parallel and perpendicular lines, which are extremely important, especially when we talk about triangles and other polygons. So to start today's lesson, instead of going directly into parallel and perpendicular lines, we'll talk about line-angular relationships. And I believe we covered linear pairs and vertical angles in previous lessons. Today, we'll just go a bit more into these kind of relationships. Our first one is a review of something we already talked about, the parallel postulate. In our first lesson, we talked about this as one of Euclid's postulates. Through any point that is not on a given line, so to visualize this, if this is the given line, through any point, so there's a point that's not on the given line, but is in the same plane. So keyword, it's in the same plane. There's exactly one line parallel to the given line. I'm really bad at drawing parallel lines, but this is my best shot. Oh my God, that actually looks good. Okay, so the definition of a parallel line, it never intersects the original line, but it's in the same plane as the original line. So now that we know the definition of parallel, we can look at this postulate in a new light. Since it's a postulate, it doesn't need to be proved. So we can accept without proof that there's exactly one parallel line to the given line through this point. Now, similar to this is the perpendicular postulate. Same thing, through a point that's not on the given line, but is in the same plane. But now there's exactly one line perpendicular to the given line. So if this was our given line, and this is the point, this is the line perpendicular, and there's only one line. Again, it's a postulate, we don't have to prove it, so we just accept this. There's exactly one. Now, a transversal is another type of relationship. It's a line that intersects two or more coplanar lines at different points. So we remember that coplanar means that they're on the same plane. So these are the two lines. They don't have to be parallel, by the way. It could be something like this. So let's just say it's like this, just so that we're not generalizing it to parallel lines. A transversal is a line that intersects these at different points. So if it went through this point right here, that wouldn't be a transversal because it's only intersecting at one common point. Too slow. Okay. So instead, we have to intersect it at different points, like right here and right there. So this would be a transversal. It intersects these two coplanar lines at different points. In this lesson, we'll mostly be talking about transversal to parallel lines, but it doesn't have to be parallel. Some important pairs of angles that we need to talk about this lesson. Corresponding angles have corresponding positions. So let me quickly draw a transversal. And let me actually make it not parallel. So there, it doesn't intersect, but it's not parallel either. I mean, if we extend it, it would intersect. So if this is the transversal, so I'll call this L, this M, and this is T for transversal. Corresponding angles have corresponding positions. Now, what exactly is a corresponding position? Well, this is the transversal that intersects with the line M. So when the transversal intersects with the line L, the exact same position, top right corner. And then there's this one, which is top left corner. That's the corresponding position of this one, top left corner. And then bottom right and bottom left. So actually, let me use different colors to distinguish these. So if these are corresponding angles, next there's alternate interior angles. So sorry that the diagram is kind of blocking the text, but I'm gonna switch to red and I'm gonna show you some alternate interior angles. it's between the lines, so between these two lines, and opposite sides of the transversal. So for example, if we still have this, this angle, then it's alternate interior angle. So it's between the lines. So it'll be right around here, but it's on the opposite side. This is on the right side, so this should be on the left side. This would be the alternate interior angle. Alternate exterior outside the lines and on opposite sides of the transversal. So new color time. If we keep this as an angle, outside the lines, actually in this case, this wouldn't work because it's not outside the lines. So just for this example, I'll use a different angle. This angle is outside the lines. It's on the outside and it's on opposite sides. So this is on the right side, the alternate exterior should be on the left side. So these two angles are alternate exterior. They're opposite sides of transversal and they're outside the lines. And then same side interior, also called consecutive interior. So this one, I'll use orange now. It's between the lines, so we can still use this angle. And it's on the same side of the transversal. So it's this angle right here. It's between, and they both are right. Then again, we can also have one left of the transversal and the other left of the transversal too. So those are the line angle relationships. And now we'll talk about parallel lines in general, or sorry, in specific. So corresponding angles of parallel lines. Let me draw a pair of parallel lines right here. This is L. This is M. And this is the transversal T. So I'll just refer to this diagram like whenever we're on the slide. So corresponding angles postulate. So all these postulates and theorems will start with if two parallel lines are cut by a transversal. So we already know that they're parallel lines and they're cut by a transversal. So we can just ignore that portion right here. We'll get to the actual postulate itself. But when you're getting introduced to a new postulate or theorem, the condition is always important. Right now, we already know that they're parallel and we know that they're cut by a transversal. So we just have to look at the theorem itself, or in this case, the postulate itself. It says that the pairs of corresponding angles are congruent. So if these were the corresponding angles, then this is congruent to this. But if these were the corresponding angles, bottom left and bottom left, those would still be congruent to each other. So any pair of corresponding angles would be congruent to each other. Alternate interior angles theorem. Notice this was a postulate. We didn't have to prove it. It was given. Theorem, now we have to prove it. And I can give you, the rest are all theorems too. So instead of proving all of them, I'll give you a proof for this. And if you want, you can prove this on your own, the rest of the theorems. Once you know the proof for one, it's pretty easy to apply them to the others. But first, the theorem itself. It says if two parallel lines are cut by a transversal, same thing. So the pairs of alternate interior angles are congruent. So we said that this and this was a pair of alternate interior angles. Now we know that they're congruent, but how do we know that? Well, we have to prove it. First, we know that these two angles are congruent by the postulate. I'm going to call this angle 1, angle 2, and angle 3. So we know angle 1 is congruent to angle 2 from the corresponding angles postulate. So this is how an actual proof would look like. So I'm giving you a sample proof just to prep for geometry class, because proofs are an important part of geometry, if I didn't mention that in the first lesson. So what we wanted to prove is 1 is congruent to 3. If you notice, since 1 is congruent to 2, if we prove that 2 is congruent to 3, then by the law that we learned, I believe it's a law of syllogism, 1 is congruent to 3. So how do we prove this? Well, if you look at it at its angle, you notice that these are actually vertical angles. These are lines that intersect, which means these are vertical angles formed by lines that intersect. They're opposite. So by the vertical angles theorem, sorry, not postulate, it's just postulate. By the vertical angles theorem, we know that angle 2 is congruent to angle 3, which means that angle 1 is congruent to angle 3. And this is either by the law of syllogism, but that's mainly for statements and conditional statements, to be honest. But you can also say like substitution property of equality. Well, actually, most of the properties of equality can lead to this. So you can just say any property of equality. I believe I talked about them in the first video. So if you need a refresher, just go and look at that. So now there's the proof. It's relatively simple, just 3 lines. Although real proof, some more complex proofs that I maybe might introduce later, they're not this easy. They actually require some thinking. Oh, oops, okay. I need to keep that diagram. So like I said, I'll only prove this one, and you guys can prove the rest on your own if you want. They're relatively simple. So it says alternate exterior angle theorem. The pairs of alternate exterior angles are congruent. So we know that the alternate exterior angles were this and this. Note that it can also be this angle and this angle right here. But for the sake of this lesson, I'm just gonna say these 2 angles. The pairs of alternate exterior angles are congruent. So you can prove it if you want, but it just involves using a corresponding angles and then vertical angles again. So you find the corresponding angle to that, you use vertical angles, and you just prove it. Next theorem, same side interior angles theorem. The pair of same side interior angles are not congruent, but supplementary. So we know that this angle and this angle are same side interior. It can also be this angle and that angle, but like I said, for the sake of this lesson, we'll just consider this. To prove that these are congruent, again, you can use corresponding angles. So the corresponding angle of that is this, and then you can use linear pair theorem. The linear pair theorem states that these 2 are supplementary. So if this is congruent to that and these 2 are supplementary, that means this is supplementary to that. Quick refresher, supplementary means they add up to 180. So it's important you copy this down or remember it either way. These are essential for geometry. So now we talked about if lines are parallel, then we can have all these awesome relationships. But what if we don't know that the lines are parallel? What if we want to find out that the lines are parallel? Well, that's where we use the converses of these theorems. And if you remember back to our first lesson, converse is basically you invert the hypothesis and the conclusion. So if P, then Q becomes if Q, then P. So in example, for example, it would be if 2 parallel lines are cut by a transversal, then the same side interior angles are supplementary. We learned that on the last slide. So the converse would be if a pair of same side interior angles were supplementary, then the lines cut by a transversal are parallel. That's proving them parallel. So corresponding angles converse if two lines are cut by a transversal and the pair of corresponding angles are congruent, then the lines are parallel. Let me just draw two lines. This looks parallel, yes, but on an actual geometry test, they might not look parallel. It'll say like figure not to scale. That's what test makers love to do. So these are the corresponding angles. And if they're congruent, let's say we know they're congruent, then these lines are parallel. Simple as that. Now, if we know that the alternate interior angles, this angle and that angle, if we know they're congruent, then the lines are parallel. Similarly, if we know that this angle and that angle are congruent, then we know that the lines are parallel. Likewise, if we know that this angle and that angle are supplementary, then we know that the lines are parallel. I'm moving through this relatively quickly because these are just the converses of theorems that we already learned. So if you want to copy this down, just pause and take some notes. Also, quick thing, this is not supposed to be the alternate interior angles theorem. It's supposed to be the converse, and same for these two. Just if you're writing this down, just change it to converse instead of theorem, because the theorem was saying if the lines are parallel, then these are congruent. And this is saying if they're congruent, then they're parallel. So just change this to converse. Now, the transitive property of parallel lines, if two lines are parallel to the same line, then they're parallel to each other. So this is slightly different than what we learned. So I'm going to clear that drawing right there. And instead, I'm going to draw something else. So we know that this line is L, this line is M, and this line is N. So if we know that L and M are parallel, and we know that M and L are parallel, which means that N is parallel to L and M is parallel to L. So two lines are parallel to the same line, then they're parallel to each other, which means M is parallel to N. I know this diagram is a bit off. You don't know which two lines are parallel, but it's basically saying that it's pretty obvious. It's basically the transitive property of equality, but with parallel lines. So we talked a bit about the coordinate plane last time. A bit more on the coordinate plane. So the slope is the ratio between the vertical change and the horizontal change. And this is mostly in like equations of linear lines. So if we have something like this, a segment right here, the slope is vertical change or rise. This is also written as delta y, change in vertical components. This change in x, change in horizontal components. So this is read as delta y and delta x. So slope is the ratio between delta y and delta x. Simple. A negative slope falls from left to right, and a positive slope rises from left to right. So it's an example of positive slope because this is the left-hand side, this is the right-hand side, and it's rising. But if I had something like this, it's falling right now because the slope is negative. This is the left-hand side, this is the right-hand side. So it's falling, therefore it's negative slope. There's some other types of slope. Zero slope is just horizontal. And you can, that makes sense because the y is not really changing, but the x is changing. So it's basically delta y over delta x. Delta y is 0 because there's no change in y. So this is just 0. Oops. And then the undefined slope is vertical lines. This is because it's delta y over delta x, but the x isn't changing. So it's delta y over 0. So it's undefined because you can't divide by 0. So if you want to compare slopes of two lines, and if you're not familiar with slope or line, just look at our algebra 2 and pre-calculus video. In the future, I'm going to post lesson 4, which is about graphs and lines, things like that. So it's not out just yet. But lesson 4 would talk about this more in detail. I'll probably post it this coming weekend. But for now, just comparing the slopes, a steeper line, the magnitude of slope is greater. So if I had something like this, sorry, that's vertical, something like this and something like this is steeper, so the slope is greater. Now, what if I had something like this? Well, in this case, this is a steeper line, but let's just say this has a slope of -2, this would have a slope of -1. So, sorry, -11, -1. So this slope is obviously greater, but what I'm saying is the magnitude of the slope, which means this has like, the magnitude of a slope is basically the absolute value of slope. It's basically the steepness. So this would be 2 and this would be 1. So this has a greater magnitude of slope, even though this has a greater slope itself. Negative numbers are tricky. Parallel lines have the same slope. If I have this and I have this, they have the same slope. Now, on the other hand, perpendicular lines, their product is -1. So if these are perpendicular, their slopes is -1, the product. So m1 times m2 is equal to -1. So something to note, all horizontal lines are parallel, all vertical lines are parallel. All horizontal vertical pairs of lines are perpendicular. So the coordinate plane itself is a pair of perpendicular lines, because this is one vertical, this is one horizontal. So some more coordinate plane. X-intercept is the point where a graph intersects the x-axis. So if this is the coordinate plane, and let's just say we have some line over here, this would be the x-intercept because that's where it intersects the x-axis. And note that this is also when y is equal to 0, because there is no y value, it's just 0. Now, y-intercept is where the point, the graph intersects the y-axis, which is right here. And this is when x is 0, because there's no x value. A line is where a slope is constant everywhere. So this would be a line because the slope from here to here, let's just say, is 2. The slope from here to here is 2. The slope from here to here is 2, and so on. But let's say we have something that looks like this. Well, the slope from here to here is vertical, so it's just undefined. The slope from here to here is, I don't know, -1. The slope from here to here is -2. The slope from here to here is 3. You get the point. The slope varies, but a linear graph or a line has a constant slope everywhere. A proportional line passes through the origin. So if this was the coordinate plane, it's a linear graph that passes through the origin. Well, this doesn't really, but I can just like smudge it a bit. Now it passes through the origin. Non-proportional doesn't pass through the origin. So it's basically any other linear graph. The slope-intercept form of a line is y is equal to mx plus b, where m is the slope of the line, b is the intercept. Yes, the y-intercept, not the m and x-intercept, but b is the y-intercept. So yeah, like I said, m is slope and b is y-intercept. A proportional would have y is equal to kx. Well, I'm just using k here because that's how it's usually written. You can also write y is equal to mx. It's basically saying that the y-intercept is 0. So an example of slope-intercept form is y is equal to x plus 3. So if you have a graph, the y-intercept would be 3. This is how you graph the line. And then you go 1 to the right, 1 up, because the rate of change is 1. The slope is 1, so 1 up, 1 to the right. You pull out the other point, and since the slope is constant everywhere, you just need these two points, and then you can graph the entire line like this. Point slope form, y minus a is equal to m times x plus x minus b. So again, m is the slope. And this time, the point AB is a point on the line. Well, actually, in this case, the point on the line is actually b comma a, because the x corresponds with the b and the y corresponds with the a. It could be written in this form. It's also written as y minus y1 is equal to m times x minus x1, but that's too many confusing variables, because like, what's the difference between y and y1? It's just saying here that x1 comma y1 is a point on the line. I honestly prefer this form. You can write down whichever one is comfortable to you. Right, like I said. And the other type of equation of a line is standard form, ax plus by is equal to c. And here it's not like a, b, and c are specific things, but you can calculate the slope. So the slope would be negative a over b, and c over b is the y-intercept. So for example, if we had something like 2x minus 3y is equal to 9, then negative a over b, this is a, this is b. So negative 2 over negative 3 is equal to 2/3 is the slope. And the y-intercept is equal to c, this, over b, this. So it'll be 9 over negative 3, which is equal to negative 3, which is the y-intercept. So if you want to convert this to a slope-intercept form, you just write y is equal to, the slope is 2/3, x, the y-intercept is 3, minus 3, and voila, now you can graph it. Taxicab geometry is a type of non-Euclidean geometry. Basically, it's saying that it's not like, what we're talking about now is just Euclidean geometry. Straight lines. The shortest distance between this point and this point is the straight line that connects them. That's Euclidean geometry. Non-Euclidean geometry, it involves the perspective of a taxi cab. And this is because it can only travel parallel to the axes. So for example, if you're in New York, then these would be blocks. For example, something like that, except it should all be uniform in size. So if I start here, I can't really cut through a block if I'm a taxi cab. I'll have to go on the street and then there if I want to go here. So now the shortest distance isn't just the straight line that connects them. Like I said, you can't cut through blocks. It has a separate distance formula too. And this distance formula, if you want to go from a comma b to x comma y, so let's say we start at a, b and go to x, y. Well, first you want to go the horizontal distance, which is x minus a, but it's the absolute value of that, because if x comma y was over here, then you can't go negative distance. So it's the absolute value of x minus y. And then you have to add the vertical distance, which is the absolute value of y minus b. And this would be the distance formula for taxicab geometry. It's not really used much in geometry, but this is just for fun. So now we finally get into perpendicular lines. So some important things to know about perpendicular lines. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So keywords, linear pair, congruent angles. So we know that a linear pair is when two lines intersect, you get this and this. If they're congruent, that means this angle is equivalent to this angle. So we know that A plus B is equal to 180 degrees because it's a linear pair. And we know that A is equal to B. So then we just get that 2A is equal to 180, A is equal to 90 degrees. So yeah, they're perpendicular because they form 90-degree angles. If two lines are perpendicular, then they intersect to form 4 right angles. So we have this and this. And we know that one angle is right because it's perpendicular. Then because of the linear pair theorem, this must be right. And because of the linear pair theorem this way, this must be right. And because of the vertical angles, this must be right because it's congruent. So it forms 4 right angles. I'm just quickly going through the proofs here. I'm not writing it down, just showing you. If two sides of adjacent acute angles are perpendicular, then the angles are complementary. So this is a relatively easy one. We know that these two sides are perpendicular, and we know they're adjacent acute angles. So this and this. So if you want, just pause and try to work out the proof, but I'll show you. I'll give you a second to pause. Well, this is an extremely easy one because we know if this is A and this is B, A plus B must be 90 degrees because the sides are perpendicular, so this must be 90 degrees. And by the angle addition postulate, you know that this angle plus this angle equals to the total angle. So A plus B is equal to 90, and that's just the definition of complementary angles. And then a theorem, perpendicular transversal theorem. If a transversal is perpendicular to one of two parallel lines, it's perpendicular to the other. We're given parallel lines, and we know that this line is perpendicular to this line. That means it must be perpendicular to this line. And you can prove that by, yes, the corresponding angles theorem. Lines perpendicular to transversal theorem. So in a plane, if two lines are perpendicular to the same line, they're parallel to each other. So it's similar to this one. It's basically saying if there's this line right here, this line is perpendicular to it, this line is perpendicular to it, again by the corresponding angles theorem, but this time it's the converse. We know that these two lines are parallel. This is basically the converse of this. The shortest distance from a point to a line is a perpendicular segment. So remember we were talking about how the shortest distance from a point to point in Euclidean geometry is the line segment connecting them. Well, if we have a line and a point, the shortest distance is the perpendicular segment. This is the shortest distance. And you can actually prove that using the Pythagorean theorem, but well, we didn't really cover it yet, first of all. And second of all, it's a bit more complicated than the other proofs we saw. And finally, the distance between parallel lines is perpendicular segment between them. So similar to the previous one, if we're given two parallel lines, the shortest distance is the perpendicular segment between them. And again, you can prove using the Pythagorean theorem, but I'm not going to. That's it for this lesson. This was an extremely important lesson in geometry, but next is even more important because it's about triangles and congruence. Congruence is the main theme of geometry, basically. So I'll post the next lesson next week. See you soon. Bye.